Hi everyone, I hope you're doing well. I'm sorry I can't be there in person to share this tool with you, but I really appreciate the chance to take a few minutes to show what it can do and how it can help us explore data through both time and space. The GenRe-Mekong project has already developed an R package that helps translate genetic surveillance data into actionable public health information. Specifically, it takes information from the spot malaria's genetic report cards and generates intuitive geographical maps showing prevalence, diversity, and relatedness. What I'm showing you today complements that tool by focusing on the dynamic visualization of the data. It's a prototype of an interactive app that allows users to explore data across time and geography. And right now, it accepts a simple data format with geographic coordinates, collection dates, and user-defined sample labels. In this first example, I'm showing routine surveillance samples from the GenRe-Mekong project in collaboration with national malaria control programs. I'm showing data from both PF and PV, and each of these samples is labeled by species. The GenRe-Mekong project was established to conduct malaria genetic surveillance in partnership with the control programs and local researchers across the Greater Mekong subregion. Our pilot began in Cambodia in 2016, and routine surveillance in Laos and Vietnam started in 2017. To give an idea of the scale, in Vietnam, the project processed about 32% of WHO reported PF infections. In Laos, it was 16%, and in Cambodia, it was 21% of the WHO reported PF infections. And here, the red dots represent PF, and the blue dots represent PV. We can clearly see that PF cases have declined, while PV has become the leading cause of malaria in much of the Greater Mekong subregion, although it too is now declining. This tool allows us to visualize that shift in prevalence from PF red to PV blue over time. When we look at the aggregated trend by country, we can see that Laos has a higher proportion of PV compared to Vietnam. At a finer spatial scale, we can also see local differences. For example, in Sekong, most cases were PV, while in Attapeu, both PF and PV were detected. Interestingly, this visualization also revealed that PF and PV can coexist in the same locations, something that was previously thought to be uncommon. Next, let's focus on PV and how this tool helps us track parasite strains. Genetic diversity patterns reveal clear regional differences in PV epidemiology, and here I'll highlight two key insights. The first is cross-border movement between Vietnam and Laos. So the PV samples were genotyped using microhaplotype barcodes, allowing us to group them genetically. Each color here represents a genetic cluster, and samples in the same cluster share at least 95% barcode similarity. So in simple terms, each of the color or cluster represents a distinct strain. Let's zoom in on the border provinces of Laos and Vietnam. In the earlier time period, we saw cluster 19 in Quang Tri in Vietnam, first detected in 2018, followed by cluster 6 in 2019. The triangles represent samples that do not belong to any cluster. Both clusters 19 and 6 spread into surrounding districts and crossed into Samoi district in Laos in late 2019 and later into Nong district. Then in 2024, we detected an outbreak of cluster 4 in Samoi, a monoclonal cluster that drove the rise in overall PV cases in Laos that year. When comparing their genetic similarity, we found that cluster 6 and cluster 4 shared 81% similarity, suggesting that cluster 4 may be a recombinant of cluster 6 and a local parasite. The clonal expansion of cluster 4 points to a possible selective advantage, underscoring the importance of close monitoring to prevent wider spread. Overall, the maps highlight that these border provinces act as key hubs for cross-border parasite flow, and that progress towards elimination will require joint surveillance and coordinated action between Vietnam and Laos. When we look at the overall samples in Vietnam, we see a peak here caused by a single cluster, cluster 3. So in this second example, I want to highlight another outbreak. This is a PV outbreak in Can Hoa in Vietnam caused by cluster 3 that was first detected in 2018 and then re-emerged in 2023 and caused an outbreak. Continuous monitoring of Can Hoa will be essential to detect and respond to such outbreak early. In conclusion, I would like to quickly summarize the features of this prototype app. First, it enables interactive exploration of epidemiological data through time and space. It allows samples to be aggregated by district, province, country, and it can highlight the labels. It gives an option for user to view genetic similarity between cluster or between groups. And this app can help identify trends, hotspot outbreaks, and cross-border transmission patterns. This is still an early prototype, and there are many features we wanted to add and change, but it shows the potential of interactive visualization to make data more accessible. Thank you very much for your attention.